Hello everyone, my name is Ashley Goodnight and this is my Lab 2 presentation. First, let's move to the introduction. The purpose of this lab is to capture the motion of an object dropped from a height, then model and compare the results with the program that predicts the object's motion with and without drag. We care about the conclusions and results of this lab in order to further understand the effect and calculations behind drag and to gain experience with both the tracker and GlowScript programs. In this lab, I was able to successfully model the motion of my object moving with greater accuracy incorporating drag. Here's a more in-depth summary of my results. Unlike the previous lab where we had assumed that there were no net forces acting upon the object, for the falling object we had to model the motion in accordance with two separate forces, gravity and drag. This drag force accounted for the error found when plotting gravity alone near the end of the motion and demonstrated how the object was approaching terminal, a constant, velocity as the drag force's magnitude approached the same magnitude of the gravitational force. Let's see the motion I tracked. This is the video I filmed of a sponge in free fall that I uploaded to the tracker program. I was able to collect the data on the right after following a couple steps. First, I trimmed the clip. Next, I calibrated the measurements using the dimensions of the post-it note. Lastly, I hand-marked the approximate centers of mass. When we plotted the y position versus time, here's the graph. Here we see the general curve of the graph. In order to predict the motion of this object, we need to make a few main assumptions. The initial position is at the origin, which matches with the tracker program's orientation. The ball's radius is the meter equivalence of 4.4 inches, the length of the sponge. The ball's mass is the kilogram equivalence of 0.07 pounds. The duration after trimming the clip was half a second. The initial velocity of 0 matches the object at rest at t equals 0. And for this first part, we are setting b equal to 0. In this next part, I changed the code. The red arrows point out where I added these main assumptions. The rest of the code is shown on the next slide. Here's the last of the code. You can see that I input the equation F net equals the mass of the ball times the acceleration due to gravity plus the expression for turbulent air resistance, v times the velocity squared. I also used the momentum principle to update the velocity and in turn the position. Let's see what the program ran. Here we can see the code created a graph visually similar to observed motion. Under the graph, the code also output coordinates for the y position versus time as plotted on the graph. In order to more accurately compare the observational and predicted positions over time, I put them both on the same graph. Here we can see now on the same plot, we can see how great the predicted model from GlowScript matches the observed motion from tracker. Notice, however, the graph becomes significantly less accurate near the end of the motion. We will attempt to account for this through drag. The formula for drag we will be using for this lab is represented by the equation, the force of drag equals the drag coefficient times the instantaneous velocity squared. This will work well for our model since near the end of the clip, the velocity was larger than in the beginning. This means that the greater the velocity, the greater the drag force, so by not accounting for it, there should be a larger error like we found. Let's work on calculating the unknown coefficient b. To estimate the drag coefficient, I essentially worked backwards. Starting from the position update formula, I calculated the final velocity. Using that value, I plugged it into the velocity update formula to calculate the net force. Then I plugged it into the expression for net force. I used these time points since this was where the error became noticeable on my graph. In order to solve for the velocity update, I needed to know the initial velocity, so I created this small segment of code which printed the predicted velocity at 0.363 seconds. With the initial velocity, I plugged in everything else and estimated that b equals 9.7825 times 10 raised to the power of -3. Here we can see the suggested plot in yellow is even closer to the observed motion. With that fixed, let's move on to the discussion questions. Do either of my models reach a constant velocity? Well, this is easy for gravity alone. No, since the net force will always be non-zero, there will always be an acceleration or change in velocity throughout the predicted motion. As for the drag model, I used the 3 final time steps and calculated the change in their average velocities, -0.176 meters per second. This is really close to 0, but not quite 0. Therefore, neither of my models reach terminal velocity. What if we threw the object downwards? Well, at terminal velocity, net force equals 0, so let's see where net force is in our code. Using the code from line 62, we clearly see that the calculation for Fnet does not use initial velocity at all in its calculation, so throwing the ball downwards will not change the magnitude of the terminal velocity. B terminal is always equal to the square root of mg divided by b. This, however, is not to say that the time the falling object would take to reach terminal velocity would not change. In fact, the falling object would reach terminal velocity faster thrown than dropped. With that, I am concluding my presentation. Thank you everyone for watching.